Welcome to another episode of the Corrosion Journal interview series. My name is Sammy Miles, and I'm the Managing Editor-in-Chief of Corrosion Journal, AMP's peer-reviewed scientific journal. Today, we're going to discuss sustainability of metals and alloys. I'm joined by Ingrid Milošev from the Josef Stefan Institute in Ljubljana and John Scully with the University of Virginia. Thank you for joining me today. Before we dive into today's discussion, can you provide a little about yourselves for our listeners? Sorry, I put you all on the spot on that one.
John, will you start?
We have to have the ladies start first and then the guest, so you have to start first.
Well, Sammy, thank you very much for inviting me to talk about this very important topic on sustainability of metals and alloys. My name is Ingrid Milošev. I'm from Josef Stefan Institute in Ljubljana, and I work for over 30 years in the field of corrosion science.
Greetings, everybody. I'm John Scully, and I'm thrilled to be here with Ingrid and with Sammy and to talk about this ultra important issue. And I'm a professor of material science and engineering at University of Virginia and the co-director of the Center for Electrochemical Science and Engineering and the technical editor of Corrosion Journal. And as I said, it's my pleasure to be here today.
Great. Now, the two of you wrote a thought-provoking perspective published in Corrosion's September 2023 issue. It looks at sustainability in a different way, beyond simply prolonging the lifetime of assets and infrastructure. So to set the stage for our discussion today, how do you define sustainability?
Well, the commonly used definition of sustainability is that proposed by the United Nations Commission of Environment and Development. And this was back in the 80s. And the commission was chaired by, at that time, the Norwegian Prime Minister, Mrs. Gro Harlem Brundtland. And actually, this commission was set to explore the causes of environmental degradation in relation to poverty of the South countries and increased consumption of North. And in order to understand the interconnections between social equality, economic growth, and environmental problems. And based on the work of this commission, in 1987, the report entitled Our Common Future was published, and it's a huge report with over 250 pages, and which became known as the Brundtland report. And it was very integrative and included various dimensions of society, like economical, environmental, and societal, aiming to face global changes, primarily related those to global warming. And the most often cited definition of sustainability and sustainable development from the Brundtland report is that that is the development that meets the needs of the present without compromising the ability of future generation to meet their own needs. And I think it's a very good definition, and today, more than 30 years later, these strategies set by the report are still of interest. According to the experts, and I can only agree with them, we are today at the critical point at which sustainable development must be established if we want our children to live in a sustainable society. And one of the very important process is to move from so-called linear economy to circular economy. So in a linear economy, we actually have the process where we mine, make, use, and dispose products, where in a circular economy, we also include reuse and recycle of the products. So we have to switch to mainly circular economy. However, today, and not only today, but for decades to come, we are still facing many problems during this transition. It is proposed that even by the year of 2060, only 2/3 of the economy will be circular, and 1/3 will still be linear. So let me just state some facts to background the discussion. In the last 50 years, population more than doubled. So from 3.7 billion to to 8 billion today. And global economy has grown fivefold, and the extraction of natural resources tripled, and the global emission of CO2 doubled. So because of all these facts, also demands for all metals are increasing continuously, jeopardizing natural resources. And it has to be emphasized that huge fraction of primary synthesis of natural resources, where oxidic cores are reduced, for example, via electrolysis, is the biggest single source of global warming and must be our research priority. So today, almost 3 billion tons of metals are produced, and the greenhouse of this production is huge. For example, iron and steel produce 10% of the total CO2 emission. That is 4 of 37 gigatons today. So CO2 is very important because compared to other gases such as nitrous oxide or chlorofluorocarbon 12, the global warming potential of CO2 and methane, for example, are lower, but they are produced in so high quantities that the effect is so much bigger. And also it has to be emphasized that atmospheric lifetime of CO2 is 100 years. So emission today are almost will last for 1 century.
Right on, Ingrid. I couldn't agree with you more. And not only are we concerned with the CO2 emissions and the consumption rate, but we now have a situation where 1.4 tons of materials are consumed per person per year. Again, mainly, as you pointed out, in a linear or throwaway type society. I just want to add that these goals for recycling that you mentioned, that would cut down on the primary production, which is, as you pointed out, the largest source of CO2. And, I just wanted to mention that while the steel releases large amounts of CO2, so do other materials like concrete, in the calcination of the process involving concrete production, there's lots of CO2 produced. And recycling is really kind of in its infancy. There's a large amount, we'll get into this more as the discussion goes on, but the large amounts of steel are recycled. However, there's still considerable energy that goes into recycled steel, whereas aluminum is recycled. Those two metals are pretty well recycled now. But in case of aluminum, the recycling process is only cost 10% of the energy if you were to do it from make the aluminum from a primary source. But while we have this situation with some gains in recycling, and we'll talk about how we need corrosion mitigation, and the materials will last longer, we will need less primary production. It's useful to point out that electronic waste is one of the largest forms of growing waste. So we're actually going in the wrong direction. Instead of recycling more, we're recycling less, because only 1/5 of electronic waste right now is recycled. Whereas, as you mentioned today, 1/3 of material is recycled, or scrap material is reused, as opposed to 2/3 from mining of feedstocks. And so we have a number of pressing issues. I should mention, and we'll talk about this more too, but also if you look at our metals-based civilization, iron, aluminum, nickel alloys, copper alloys, magnetic materials, 75 years ago, those typically, like your typical steel alloy, contain 2 elements. Aluminum alloys contain 3 elements. The Wright brothers, their engine casing was an alloy that included aluminum, copper, and silicon. But now, today, most of these materials are used in more sophisticated alloys that actually use a larger fraction of the stable elements in the periodic table. And the typical use is on the order of 8 elements are typically used. And those are, over the last 100 years, there's been so many gains in material science. They have some function. Those minor elements do something good for the properties of the material, but we also have to think about what you started with, which is the consumption of the resources, such that we don't have a sustainable circular economy.
Thank y'all for that descriptive background on sustainability. piggybacking on something just mentioned, how does corrosion fit into the conversations on sustainability?
Well, I think corrosion and corrosion protection is a very important part of sustainability and sustainable development. And we can contribute a lot as a corrosion scientist. If we just continue with CO2 emission, I mentioned earlier, and that the highest production of global carbon is produced by iron and steel, we must also consider how much CO2 is produced to replace the corroded parts, since corrosion affects also the lifetime, affects the lifetime of metal products. And this was recently calculated by Januzzi and Frankel, and it was calculated that if the total annual global steel production is around 2 gigatons, then the annual production to replace the corroded steel is between 3 and 650 megatons, so between 15 and 30%. And this has an additional impact on the global effect on steel corrosion. So corrosion protection reduces the amount of primary production of steel required to replace corroded parts and reduces the global carbon footprint, which is around 2 tons per single ton of steel, which is almost around 4 gigatons manually. I'm giving you these numbers just to, to comprehend the waste amount of the tons and elements we are talking about. And just mentioning the costs of corrosion, these are quite, generally known topic. And it's usually mentioned that costs due to corrosion amount to more than 3% of gross world product, which is over $2 trillion US dollars. So it's a huge amount. And this is just direct costs, like to manage and mitigate corrosion. And then there are also indirect costs, which may be as high as this direct cost. So protection against corrosion is necessary to ensure a safe and good operation of metals and structure, but also to assure the long-term effectiveness and to be at the same time environmentally and economically acceptable. And as a corrosion science, we can contribute to many steps, if not all steps, of this circular lifetime. So from mining, designing, making, using, reusing, and recycling. Maybe mining is mainly in the domain of mining engineers, metallurgists, geologists, and so on. But also the first step, like design, we can contribute a lot because by choosing optimal materials and application, but also using modern methods like integrated computational materials engineering, ICME, which refers to a holistic methodology for designing materials, processes, and advanced products. Also, we can use secondary produced materials, as John mentioned. So we have to increase the percentage of scrap so in secondary materials, and introduce less sustainable and less critical methods. Of course, materials of primary and secondary productions should be of similar quality, but maybe the exact composition or some presence of impurity can affect the corrosion behavior of this material. So this is one of the research subjects which is also open to study and to approach. Then when selecting materials, we can also use high entropy alloys to obtain desired properties of the materials by the combination of multiple principal elements in high concentrations. And today, several high entropy alloys have already been known to possess exceptional properties, exceeding those of conventional alloys, and probably more will be investigated in future. So just to mention a few of these ideas, and maybe John can continue.
Yeah, those are all so certainly essential and important things, but corrosion also plays a big role in mitigation strategies of, I'll call it legacy materials, or materials that weren't designed with corrosion in mind. And there tend to be a number of mitigation strategies. Everybody in AMP knows about these, but coatings, corrosion-resistant alloys, post-treatments, electrochemical protection, which many of you know is cathodic protection, inhibitors, and then even things like greases and oils. And just to give an example that it's a challenging issue, that what the CO2 you're saving is going to be is challenging. Just consider a thermal barrier coating. This is an example that Ashby brings up in his textbook, but our thermal barrier coating on a jet engine and a turbine material, takes a lot of CO2 to produce that coating. There's an enormous amount of CO2, but there could be a gain if the plane flies safely and the engine life is increased and it can fly faster or higher altitude. Bigger difference, bigger delta T is a more efficient energy. And so the cost of the materials for corrosion control is what I'm saying is could have a large embodied CO2, but it's really it's a complicated discussion as to how much CO2 is really factored into if it needs to be replaced. If it needs to be replaced or it needs to be relocated somewhere else, there's huge investment in the repair costs and in the maintenance. And so the corrosion field, just for instance, that 15 to 30% of steel is replaced yearly. And so you encounter that embodied CO2 costs. But I'm not sure that any of the calculations are including the total cost, the indirect as well as the direct costs.
Yeah.
And so there's just lots of benefits in corrosion. As Ingrid had mentioned, I think one of the things is all the exciting materials that are coming online, and not just additive manufacturing versus subtractive manufacturing. We can generate a lot less CO2 if we use near net shape. This is an old word, but now it's very appropriate for AM, for additive or 3D printing. If we can design materials without much wastage, then we, in theory, are generating less CO2. And so the idea of tunable materials that have the right properties at just the right spot, I'll talk about this more later. And so every time a new material is introduced, we need to talk about its corrosion and make sure that we don't take 2 steps forward and 1 step back. Just as one example, that if we do increase recycling and scrap, and I'll end with this point, but just one example of that is that we need to understand what recycling, if you recycle something 4 times, what are its corrosion properties as well as its other properties like mechanical properties? What are they going to be? And some of these are uncharted territories where the corrosion field can really step in and do its part to make sure that recycling is viable without a loss in properties. Right now, we don't design materials. Typically alloying elements are added, as I mentioned, for this increased functions that we want and better properties that we want. But they're not, only a few people are considering what I would call recycle-friendly elements. Or how can you trick a material to take an element that is not expensive or not scarce, but also does the same job? That requires people in the corrosion field to research these issues.
If I may add, just what I think it's also important is the include modeling and also machine learning techniques and artificial intelligence, remote sensing, and so on. So all these techniques contribute to produce less CO2 and to use less chemical and to prepare ourselves in advance to make experiments. So
right, absolutely, Ingrid. In fact, if you didn't mention that yet, but if you consider all the attributes, if you're good at design a material and you have a lot of flexibility with additive manufacturing, let's say, with both the thermomechanical processing as well as the elements that you use, then there's too many attributes, too many variables to test all those out, and so we're going to need integrated computational materials design and machine learning, artificial intelligence, in order to sort through all the variables to arrive at a workable alloy. There just won't be, even with autonomous or semi-autonomous testing, it will be hard to factor everything in. And so we'll need every bit of artificial intelligence that we can get our hands on. And the corrosion field has actually historically been fairly adept at picking up on recent developments pretty quickly. And then this is another example where that'll be necessary.
Absolutely, very exciting field.
Now, what are some of the areas that people haven't been focusing on that need additional attention? I think y'all touched a little bit on this in that last question, but Ingrid, do you want to get us started on that?
Yes, thank you. Well, just to mention that, in my opinion, all these steps of circular economy we mentioned before, mine, design, make, use, recycle, need additional attention. We are facing severe challenges regarding global environmental pollution problems and potential lack of resources that we have to work together on, not only in each research field separately, but especially inter and across disciplinary to address this critical issue we need to solve. And before all, we must become aware of these challenges and bring the attention of the community to step together and do the best we can. And I think it's each person's responsibility to behave sustainably and live in equilibrium with his or her needs and carbon or waste footprint bring to the environment. And this means that we have to align with R and D principles. The more letters R and D's, the better. So what does R stands for? And I mentioned this several times, like reduce, reuse, recycle, implying the use of fewer resources, using material more than once, and converting the waste into product. And recently, 10 levels of circularity were introduced by Professor Kramer from the Utrecht University. So, and these are just to list them briefly: refuse, reduce, renew, reuse, repair, refurbish, remanufacture, repurpose, recycle, recover. So there are a lot of R's here, and all these are focused to, use less and recycle more. So what does the D stand for? And the broader concept of material stewardship was recently introduced as a concept of improved materials conservation through a 4D strategy: dematerialization, durability, design for multiple life cycles, and diversion of waste streams through industrial symbiosis. And this was introduced in the book by Corrosion Management for Sustainable Future, edited by Taylor and Sanchez-Sor. So I think as engineers and scientists, we face much higher responsibilities to contribute to a more sustainable society by inspecting and reconsidering each step of our work process and always looking for environmentally friendly solutions, or at least those who make minimal impact at highest efficiency.
Well, the corrosion field has always had a parade of challenges that it's addressed. And, just coming back to pretreatments a little bit, there are things like chromate replacement and heavy metal replacement, and even in biofouling paint and tribunal tin that have been issues that have been challenges for the field to overcome. I think we were talking about artificial intelligence. I think inverse engineering or inverse design needs to be considered, where we basically say we still do, even at the lifetime prediction in integrated computational materials design and CalFab processes have been revolutionized. You can use this free software, the Materials Project, to do a Pourbaix diagram as fast as I just said that. You can do a Pourbaix diagram. But I think that we need to harness everything that's happening in the materials science field to look at because we can't just say, okay, well, this will have a lifetime of 100 years. Okay, so now it's time to celebrate and stop there. We can't just stop there. We have to be able to precisely say, what the lifetime would be, what the trade-offs would be, maybe a scenario analysis. If you paint now, or you protect now, or retreat now, versus doing it 10 years from now, what will be the benefit? And I think one of the problems is that's those CO2 calculations, as well as the materials performance calculations, are kind of still, as much work has been done, they're still in their infancy, in my opinion. where they still need more work because we're not able to say, how much CO2 we save by using this paint. We talk about steel corrosion, for instance, as something as basic as that. One of our primary, if not the primary engineering material today, still in this world. And we can change the CO2 footprint, the CO2 embodied, by just understanding how much CO2 we introduce by adding an organic coating, and then how much CO2 we introduce by adding a pretreatment, like say galvanizing. And so there are papers that have come out. In fact, I have one, I think we cited it in our article in Corrosion and Sustainability, but one by Atkins and Lambert that talks about sustainability of steels and talks about the lowest CO2 footprint. And it's surprisingly certain combinations of galvanizing and certain combinations of coatings arrive at the lowest CO2 footprint in total. When in some cases, it turns out shockingly, you'd rather let the steel corrode and replace it than adding the coating. It was illuminating for me, but the coating could add so much CO2 to the equation that you had to basically carefully optimize it. And now those optimization tools don't exist. If you were to say to someone, okay, a piping distribution line, not a transmission line, this is right in the center of AMP's interest, a distribution line made out of PVC, polyvinyl chloride, piping, made out of copper piping, and made out of lead piping. Okay, go. Which one, cradle to grave, gives you the lowest CO2 footprint? That's a calculation that corrosion engineers should be able to do. And only the corrosion research and development, testing, evaluation community will be able to provide those answers.
And on top of that, those challenges you just mentioned, are there any others that we're running into as we are trying to improve the sustainability of our resources and infrastructure?
Well, as I mentioned earlier, we need to do inverse design, not only artificial intelligence and sort of design forward, but inverse design. The other thing is, I think there's probably a blurring that's going to happen that we're revolutionizing the materials field. There will be a blurring between, it has to be, it actually factors into this recycling and reuse issue, but the blurring of the line will be between developing the material as a totally separate item from developing the design. And what I mean by that is the way it is today is you say, I have this design, I need this strength, let's say, this strength and this corrosion resistance. This got to be this strong for 10 years. And now we say, okay, here's your off-the-shelf material. You don't like it? You don't like the properties of this material? Okay, pick another one off my off-the-shelf list. But now, what needs to be this inverse engineering where you are able to tune backwards and say, I got to have that strength after 10 years. What do I do to get that in terms of the material line? So design, it's happening already in additive manufacturing, but I think the boundary between material or coating or pretreatment and the design are treated separately. Basically take the list of materials that have been made, and you have to pick one, right? And you pick one based on the location on your component. If you're making a component, you might pick the material because, I need a hard surface right here just on this one part where it touches. So I need a hard coating. But, okay, well, pick the hardest material off the shelf that you can build that component out of. You might say, well, no, what I'd like to do is I have like a spot on there that's additively manufactured or some sort of, there's all kinds of coating and exotic treatments. We see them on the AMP showroom floor during the conferences. There's all kinds of ways that you could take just that one spot and make it more corrosion resistant or harder. And I think those kind of things will come with time, but I think that's one direction the corrosion community should go.
Ingrid, are there any challenges that you want to bring up?
Yeah, maybe I will talk, maybe I will address this part on resources in this question. So for me, the eye-opening moment, so to say, was reading the papers which describe the possible depletion of metal resources in the 21st century. And in our everyday lives, we usually read about, greenhouse gas emission effect, about global warming, microplastic pollution, lack of precious metals, need for reduction the use of fossil fuels. all these issues are concerning, of course. However, what is not commonly presented to general public, I think, is that the given continual modernization is boosting the consumption of metal despite the need to transition to a low carbon society. And even more, that this process seriously jeopardizes metal resources of common metals we use. So for me, this was shocking because I learned that maybe we will run out of copper ore by the 2050. And, you know, what will we do without copper? So although the use of solar and wind power technologies is green, making them is not. And this is pointed out by Professor Dirk Rabe from Max Planck Institute in the recent excellent paper in Chemical Reviews. So why is that? Because the transition to a green society will enormously increase the consumption of metals, which is estimated to be 200 to 300 that of fossil energy plants. And these are really big numbers. So the demand, it is calculated or predicted that the demands for major industrial metals, including iron, aluminum, copper, zinc, lead, and nickel, will increase 2 to 6-fold by the end of this century. And there are many prediction and estimation. These are very complicated calculations, but we also pointed out in our paper some highlights. The calculated demand for each of these metals will double or triple relative to 2010 by the mid-century. And then the second, in the case of copper, zinc, and perhaps lead, supply may be unlikely to meet demand by 2050. And thus, this poses an immediate concern. For nickel, iron, aluminum, and manganese, the resources are not expected to exceed their resources to mid-century values, so imposing no immediate concern. However, here we also have to mention the increase in energy consumption, and it is predicted that it will increase up to almost 40% because of transition to green technologies. So many authors now emphasize also so-called rebound effect, which is a result of this paradox I mentioned at the beginning. So limiting global warming requires a huge growth in renewable energy sector, but on the other hand, this creates a rebound effect, which causes a further increase in greenhouse emission instead of its reduction, because we have to produce more and more metals, produce more and more green gas emission, and the effect is not expected to change by the, I don't know, several decades from now.
Right. Just to pick up on Ingrid's point, I totally agree with that. But if you just take our energy solutions and our sort of renewable energies, we really need those solar panels to last longer. They have people talk about lifetimes and I guess in tens of years, but and the same with nuclear power. If nuclear power is going to be a part of our clean, abundant energy solutions, there's so much CO2 created, as I mentioned earlier, in the concrete and the steel that are used in the nuclear power plant. So I don't know the exact number, and I'm not a nuclear expert in the nuclear field, but if you look at a nuclear power plant, if it can last for 60 years or 40 years, 60 years, 70 years, then you get beyond break even, where you save a lot more CO2. Same with the solar panels, you save a lot more CO2 than you expended embodying, and building that structure. But I'd also like to point out, as I mentioned in the beginning, not to be sort of a pessimist about this, but that we're actually going in the wrong direction right now. And I'll bring up just 3 examples, just some fun facts for our listenership. The light bulb. It used to be old light bulbs were the only precious material was really the tungsten filament, and the old light bulb used some readily available materials and some glass. So there's only one material in U.S. Geological Survey critical list. Now there's 6 elements used, 6 of the elements in these new high-performing, long-lasting, it's great, high lumen light bulbs now have 6 critical elements, or 6 elements that are on the U.S. Geological Survey critical list. Phones, as you know, with your smartphone, 52 elements now versus 9 elements, right? The old, those 52 elements, the old one, only had the copper, which is important, as Ingrid mentioned, but nevertheless, just copper was the only thing that was precious. Now there are 21 of those 52 elements that are on the U.S. Geological Survey critical list. Same thing for jet engines. Old propeller airplanes, maybe 9 elements, 1 critical. New airplane engine, jet engines, 24 elements, 9 are critical. I won't be able to get the response from you, but I'd like the audience to tell me about what do you think of flat screen TVs? Everybody in every home has at least 1 flat screen TV. Some of us have more than 1, right? How many elements do they have, and how many are on the U.S. Geological Survey critical list? Flat screen TVs are sold everywhere, made by many countries. 30 elements on the periodic table, and 13 of those are on the critical list. So we need to find, the challenge is to find, substitutes, also increase the recycling and reuse of these devices. And, we have this increasing amount of electronic waste, as I mentioned earlier, and that's why this is happening. We probably need some things in our society to change. Phones are probably reach obsolescence now, smartphones, based on capability and based on model number, and not necessarily based on whether they could actually be used or not. The obsolescence is really not defined as we think of it in the corrosion field. Recycling will be a challenge because you're looking at getting maybe small amounts of cobalt out of that iPhone or cell phone, and you're looking at a large amount of material like plastic and whatnot, and a small amount of cobalt that would be highly desired. I just wanted to mention the gold thing, as I mentioned once before, is that there's more gold, and to get 1 metric ton of gold takes 17 tons of gold ore, but you can get 1 metric ton of gold out of so many computers that are recycled. And so to face this situation that Ingrid talks about our resources available at mid-century, we're going to have to consider really an all of the above solution, because it probably won't be just one thing. Corrosion control plays really big in that area, I think, and we can talk about that some more. We have interjected, I guess, injected some parts of some good corrosion thoughts in here, particularly for my colleague Ingrid.
Thanks. And do you have any final thoughts before we wrap up?
Thank you, Sammy, for very interesting questions, and I thank John for discussion. I just maybe would like to say at the end that as corrosion scientists, we usually investigate fundamental scientific issues regarding corrosion mechanisms and solutions to mitigate a specific type of corrosion for a specific application. And we may have background education in chemical engineering, in chemistry, metallurgy, material science, mechanical engineering, whatever. We don't have a background education in sustainability or sustainable development. But in our research, we need the knowledge of all these disciplines. So I think we should expand our focus from the immediate subject we are working on and always try to put it in the framework of principles of sustainability.
Yeah, here.
That's well said.
Also, very well put. I would like to say that yes, there's a matter of us broadening ourselves, and one of the areas that we didn't mention today, but mentioned in the article, is the use of ionic liquids or designer solvents to selectively remove, long story short, but hydrometallurgy and pyrometallurgy, which were developed originally for another purpose. They were developed to extract from ores elements that were in low abundance. But there, things like leaching and other processes to recover elements from recycling could use some attention at the corrosion field, because it's really the same principles we have in dealloying. But there's a promising future. The corrosion community has always been quick to pick up things. And so I'm looking forward to seeing these advancements start to come out from various places. I do want to just add one comment on education, as well as the need to, we can't probably just broaden ourselves without some education. I think schools are slowly starting to move in this direction. In my corrosion batteries and fuel cells class, we now include recycling and talk about some select electrochemical processes. And what you're seeing is we're seeing more sustainability first starting not as standalone classes, but as classes where a section of the class, like 1/3 of the semester or 1/5 is dedicated to sustainability. And so I think that needs to be something in engineering classes that's more generally the case and not something that's included as an afterthought or maybe take a technical elective. So with that, I think we actually have a bright future but not without its challenges. Thank you both for having this conversation with us today, and we really appreciate Ingrid's co-authorship here. And Sammy, thanks for your organization of the event. Thank you.
And thank you both for joining me. If anybody wanted to follow up with you later, what's the best way for them to get in touch with you?
Oh, just my email, JRSAD, D is in Delta, @Virginia.edu. Happy to take comments or questions.
Yeah, same here. Just send me a mail, ingrid.milošev@ijs.si.
Wonderful. And with that, I'm Sammy Miles here with Ingrid Milošev and John Scully, and thanks for listening to another episode of Corrosion Journal's interview series. You can subscribe to AMP Podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can also find all episodes of AMP Podcasts on amp.org. That's ampp.org. We'll be back soon with another episode. Thanks for listening.